So today's topic is in fact on members and connections that are loaded in tension, of which there are quite a few. So we're talking about things like hangers, braces that are in tension, which is not unusual in industrial buildings where we design as tension-only bracing systems, and especially the connections, because that's really where everything starts falling apart. At least that's what I've noticed. So this topic is very interesting in its own right to me. I hope you also find it interesting.
Fantastic. Okay, so we have had a few more people joining us and some in the waiting room. I'm going to be admitting people as they come in. For those of you that have just come in, if you have any questions, please do pop them in the chat. We'll try and get to some of them as we go along. I'm going to be asking Amanuel a few questions. If there's anything we don't get to, we will follow it up in a subsequent session, or we may write a blog post or an article about it and put it on the Institute website. So, Amanuel, let me get to my first question. Why are tension members so popular? Tension members and connections so popular? What is the big deal about this side of steel construction?
Yeah, so why we get these questions a lot, I think, is because a lot of engineers are always trying to achieve a great deal of efficiency in their design. And believe it or not, the most efficient member that you can design is a tension member. And what I mean by that is where you get to carry the most force for the least amount of material used. Steel is very good in carrying tension. We use it in tension all the time, even when you're designing concrete. In fact, concrete does not work without steel. And what the steel does in concrete is carry tension. So all the way from concrete to structural steel to cables to let's call them catenary structures, tents. All these structures are essentially loaded in tension. And of course, that might explain why it is that we actually see many questions come in on tension members. And of course, designing a member in tension is not very complicated because in a way, it's not vulnerable to buckling or all these complicated limit states. You literally take the area, you try to find out what the strength is from somewhere, maybe the red book or your own testing, material supplier specifications, and then you divide, you multiply your area by the stress that's allowed, and that's how you come up with the capacity. So it's very simple to design. The problem arises when it comes to connecting them, and that's why I said that's the most interesting aspect of design intention, which is the connections.
So, Amanuel, are there any special quality issues that come up when designing connections in tension?
Yes. Unfortunately, where we get engaged or where questions come in is after a quality problem has already been experienced, and sometimes even a failure. So on a recent, and maybe we'll discuss it later, but there was a large design problem in one of these new power plants where there are all these things that are hanging off of, it doesn't matter what they are, they're essentially things that are hanging off of a support structure. And the hangers were having issues because of how they were connected. So there are a number of quality issues that come up. Today, we're mostly discussing bolted connections. But even when you're welding these connection types, there are specific requirements for how much work you have to put into making sure that the quality of the welding is correct, as opposed to all other types of welding that we do where visual inspection is sufficient. So yes, there are quality issues that come up. And of course, when these tension connections do not work, it's a big problem because typically they're carrying critical infrastructure.
So, can you tell us a little bit about block shear failure? What are some of the issues around that?
Yeah, so that's one of the, let's call it, more typical types of limit states that people find difficult to check. Maybe what I should do is illustrate. I don't know if I can share my screen. Am I allowed to share my screen, Denise? See. Just checking.
You should be able to share.
Okay, cool. So I'm just opening my a whiteboard that I just drew up now. So if you have I hope you can see my screen. So if you open yes, if you have a structure of this type, and this is as a very simple hanger, and we might even have 2 rows of bolts here. So let me do something that's a bit more realistic here. Oh, all right. Let's draw. Okay, this was all the way down here.
Right. So while Emmanuel is drawing there,
Oh.
just for those of you who have just joined us, if you have any questions, just pop them in the chat. If we might get to them during the session, but if we don't, we will address them in subsequent sessions or in blog posts.
Okay,
Go for it, Emmanuel.
So if I have a connection of this type, and let's say I have bolts here, clearly my mouse drawing method skills are not very hot. So if I load my structure of in this way, and this is a good opportunity for people also to pitch up on how one would address a connection of this type, which is presumably quite simple. And the question of block shear is a failure limit state. So everyone is familiar with designing, let's say, this plate here. Let's look at this plate, the inside plate, the smaller guy, for shear along. I'm not even sure if I can change my thickness here, but for shear along, let's say, this zone, which is in yielding. So that would be in yielding, and you'd essentially just check that member for tension in yielding. Then a different question might come up, where you say, well, what do I do for shear or tension through this area, which is right along the bolt holes, because that's a reduced area, and typically would check that for fracture limit state, which is essentially an ultimate limit state that checks for essentially tensile rupture on that net area. So people are quite familiar with checking these types of limit states. And they tend to figure them out quite well. The problem arises when it comes to checking limit states that are a bit odd. So for instance, there are limit states of this type. Now, maybe Sarah covers this in her class, and people who do connections design course with us, or I also do lectures at WITS for the postgraduate course, sometimes also with Sarah. So we address these types of limit states, which are called block shear. It's a very odd type of limit state, in that what is going on here is a portion of this block here. Let's see, in this particular case, okay, I gotta keep going down here. Sorry, my lines are not very straight. Oh, that's not right. Let's go back again. These are always the types of questions that come up. There we go. I've drawn it the other way. Here. This is what happens when these are impromptu talks. There we go. Okay. So even those of us who design connections all the time have to think about these things very carefully. So if I load this plate in this way, and I'm talking about this bottom plate now, what I might have, a failure type that I might have, is where this block of steel here that I have just circumscribed with my straight lines can actually break out and fail. Now that is called a shear block failure limit state. And what that is essentially a limit state where a portion of the plate is failing in tension. And these are these 2 lines here. And maybe I should draw them with a thicker line. Let's see here. There, there. And then my 2 thin lines are failing in shear. That's the model that we use. These failure limit states are actually much more complicated when you test them in a lab. But this is the model that we use. And we say, all right, so this is failing in tension, this is failing in shear, and the combined failure is called shear block failure. This is a real failure limit state. It's been exhibited in real structural failures, and as well as in a lot of tests. Now, when you check for this type of limit state, the capacity is in many cases is much lower than when you check the previous limit states that I described, which were yield across the whole plate or tension through the net area, what's called tension through the net area. And this is particularly interesting because this is not the only block shear limit state that I have for this configuration. So for instance, it's quite possible that I could have a block shear limit state, let's see, of this type. And in fact, of course, the symmetrical other side is also possible, where I have a limit state of this type, and I can get rid of these two here, and of this type, especially when this inner plate is actually, let's say, quite narrow. And these limit states are the ones that almost always control and are, I would say, neglected the majority of the time in checks. So this is what block shear limit state is. We try to cover it in a lot of our connections courses, but it is not clearly adequately covered in a lot of steel courses or industry level courses, and of course that's why it might be neglected. So just to illustrate what block shear is, and there are many other patterns. So if you guys want to play together later on, if we have time, we can actually go in and explore all the different block shear limit states for even a simple connection like this one. And we can look at which ones are real, which ones are not, and just figuring out the block shear limit state patterns in itself is a skill set that you have to develop. As you saw when I started out, where I was drawing it essentially the wrong way around.
Thanks for that, Emmanuel. One of the other questions that I also had there, which I'm sure some people would like a little more information on, is can you give us a little bit more insight into shear lag? What's notable?
Yes. So shear lag, so you're putting my knowledge to the test here again, Denise. Okay. So let's just delete all of this. Clear this out. All right, so if I were to draw just let's say an angle, so I draw this angle. All right, so I'm drawing an angle here. Please ignore my the problems associated with my okay. Oh, okay, like that. All right, so I'm just trying to draw a plate here. All right, so if I were to do this, and then of course, let's say this is connected using bolts. And obviously this is in tension now. All right, so if this is loaded in this way, and you have 3 bolts, typically the way, so this is an angle that is essentially attached to a plate, and this plate obviously is attached to something rigid. Assume that's the case. Then the problem that we face is that this angle, if we look at it head on, looks like this. And here's our plate that is attached to. Oh, all right, and here are our bolt holes. You can see that the centroid of this angle is actually here, right here, if you were to calculate the centroid. So when you apply a tension force into that angle, the load is actually applied right at that location, whereas the connection is actually out here. So what you have is you have this kind of eccentricity between how an angle is attached and where the centroid of the angle is. Let's call this E. All right. Now, this is the most typical way in which we attach angles. By the way, this doesn't have to be bolted. It can also be welded. What this does is it actually produces additional forces to tension in this member. So shear lag is in fact additional unanticipated forces that you would get in your angle from the way in which you're connecting it. So this is typically unusual because whenever you take your software analysis program and you analyze members, it assumes that all the members are loaded through their centroid. That's why the structural analysis software is actually, in that sense, very dangerous. Because what it doesn't account for is the fact that the way you connect the member to something will actually induce some other forces. In this case, it could be bending. You could represent it in many different ways. We call it shear lag. And what that means basically is that it will take a while for the load to go from here, which is where the bolts are, and that's how we check the bolts, let's say for shear, into the member as a whole, which means the force has to make its way all the way into the other leg of the angle. And that transfer of forces from where the load is supported to where the load is introduced out here is called the shear lag area. And of course, the shorter this dimension here, this connection dimension, the more severe that shear lag. So this design of this member, you can't just go and say, all right, I have my area, I have my yield strength, which is 355, let's say, on a larger angle, and take your 355 times, let's say, 0.9 times area is equal to my tension capacity of that angle. That is actually not correct, simply because the way in which you're connecting it, and this is the most typical way in which we connect angles to supports, will introduce additional forces. That's what we call shear lag.
Good. Right. So my final question, and then I'm going to open it up to the floor, and perhaps there's some questions or comments from Rob and Sarah specifically. Can single bolts or pins be used to make connections and tension? Can you speak a little bit more about that, Amanuel?
Okay. So in fact, the question, the problem that I was addressing earlier, which was on it was at Medupi. This is the large power plant that they're putting up, that they should have been done with years ago, but they're still putting up or trying to fix. They have hangers for some equipment, and they used single pins in the connections. And the problem was, again, it has to do with eccentricities to some degree, where essentially they have rods that are lapped like that. And of course, when you load it in tension and you have lapped two plates, again, you introduce eccentricities into those members. That in itself created problems for the engineer in the design. So meaning that they didn't account for those effects, and of course, then they had problems. But in general, using single bolts or single pins is not a good idea from an erection point of view. And this is also something else that they faced. Because the way in which riggers erect structural steel is they'll try to line up one set of holes, and they'll put a spud wrench in there to try to line it up and to put a bolt in the second set of holes. So if you don't have a second set of holes in your connection, it's actually also very difficult to erect. So in that sense, there's also a problem from just a practical erection point of view, which they also faced, that they tried to address in some other way. So I'm not a big fan of using single bolts, meaning there's no prohibition in the codes. In fact, in 10162, we have a provision for the design of pins, which is slightly different to how you design bolted connections. So despite the fact that there's no prohibition, I'm not a big fan of it, simply because there are various issues that come up that a lot of engineers are not familiar with. And also it becomes a headache for the erector when they start working on it. So these are also the kinds of questions that we see a lot, where people are struggling on site, let's say, to put up something because someone has specified a single bolted connection. They try to find remedies for how to actually fix it.
So just before I hand over to some of our participants to ask questions, Amanuel, are there any other common questions on this topic that come up from some of the calls that the SAISC receives, or some of the technical request emails that come through? Anything that really stands out for you that you think would benefit our participants here to know about?
So the one that we've seen a lot is where people are designing, and this is not really exactly a bolted connection problem, but where they're welding, essentially doing butt joint connections intention, and they want to know what type of quality control regime they should specify as engineers. That's because these are considered critical, and especially when they're what's called cyclically loaded. What that means is if it's carrying a machine or something that moves, if it's in a bridge application, where there's essentially a risk of fatigue fracture. So the question is, how good a quality of weld do you need? And is there any way to evaluate it just visually, or do you actually need some sort of non-destructive testing? So a lot of engineers are always very keen to know what to specify, how often, because sometimes there are thousands of these connections in a single structure. And there's a lot of curiosity about that, and a lot of, let's call it, confusion about what to specify for those types of welded connections in tension.
Okay, I'm going to open it up to the floor. If you do have a question, if I could ask you to just put your camera on. I will call on individuals that do have their cameras on, just so they can have a little bit of structure going here. Let me see, who do we have? Rob Pietersma, do you have any questions that you'd like to raise on this particular subject?
So thank you, Denise. I don't have any specific question, but you know, when I saw this invitation and it had the word bolts in it, I thought, well, I must attend because I'm involved in that business. Just a few comments I could give. First of all, I think that the goal or the ideal is to have connections in tension. And I think, first of all, there's the one standard, I think it's SAISC 100084 or 64, which goes into quite a lot of the preparation and what one wants to achieve. And that's a very, very good standard. It's been recently updated by the Institute of Steel Construction. The other standard, which is a very important one, which was introduced probably about 12 years ago, was EN 14399. And that was a new standard that replaced the SAB standard that existed in South Africa. And it was very important in the sense that it introduced a new element, which was the assembly testing. The assembly testing is that a bolt, nut, and washer were suitable for tensioning and had to go through a process of testing to ensure that the criteria were met. And that was very important because it then led to the whole aspect of lubrication. And you'll find typically on site, the whole aspect of lubrication is not understood. And so a bolt assembly that's torqued without any lubrication would get a lower amount of tension than a lubricated assembly. And if one is wanting to make sure you achieve that tension in the connection, it's important to make sure you're then also tensioning according to what the manufacturer's recommendation is or what the standard is. And here it goes into the next leg, which we found was quite a problem up at Medupi, is the whole element of training the installers who are going to be doing the tensioning. So in terms of achieving your end result, it's important to understand the assembly you're using, the coefficient of friction in the assembly, and what is the amount of torque required to achieve that tension. And that whole aspect is one which is really probably not understood sufficiently on site. And that's the area where we've encountered most of the problems. And it's important to make sure that your installers are trained and understand whether they're using the turn of nut method or torque wrenches which have been correctly calibrated. So that's just something that I can add.
Great, thank you very much for that, Rob. Amanuel, do you want to respond to that?
Yes, so Rob is referring now to what we call friction grip type connections, which are quite popular in various different applications. In fact, Denise, we have to remember to invite Rob for our session. I think we have one on bolts at some point. because he's literally a wealth of knowledge regarding bolts and all the. I mean, he spoke maybe for 2 minutes here, but he actually addressed a very large number of things, which are very easy to miss, especially relating to the new standards in South Africa for bolts. So friction grip connections are a very key, let's call it, tool that the engineer has when designing members in tension, especially if there's a need to avoid, let's call it, any movement in that connection in the service condition, even at the ultimate condition in some cases, but typically in the service condition where movement is not desirable. And when doing that, this is a very good topic that he has raised. The two plates that come together that are going to be essentially clamped together by the bolts, clamped hard enough that they actually will hold each other in friction, as opposed to where we typically load the bolts in shear, which is a different type of mechanism, which is called in bearing. There's also a whole bunch of specification, not just in terms of how you tighten the bolt, which is what Rob is addressing, but how you prepare what's called the faying surfaces. These are the first surfaces that are in friction. And there's also a lot of questions that come up on that topic. So I'm glad that he raised it, because people always want to know what you need to do. What is the special stuff that you need to do on those plates? Can galvanized plates be used as friction grip connections, for instance? No. Or a painted surface, or if there's rust. Boy, there are questions that come up on this all the time, and in many varieties. But Rob is also correct that questions come up about how to tighten those bolts. And of course, people love to use these torque methods without any calibration, which is what I think Rob is alluding to here. And we get also a lot of those questions. So this is actually a huge topic of discussion that would be interesting to delve into even today, the friction grip type connections.
Liz, I see you have your camera on and your hand raised. Is there something that you'd like to address?
Yeah, I'm just thinking the 90. I would say let's say 80% of most connections that one has worked with is in shear. There's no tension, it's just in shear. It's like you can put your finger in there, and if you're strong enough, it'll hold it. So what? If the bolt is left loose, it doesn't make any difference. As long as it doesn't fall out, it's fine. So why are we going down this road of tensioning bolts and bolting them and tightening them to the nth degree? In the most cases, is nonsense. You could stick a peg in there and it would work, and it doesn't need to be tightened. The only time you need to tighten a bolt and put it into tension is for a moment type connection where you're getting prying forces and it's trying to pry the parts apart. That's when you want a tension connection or a tension bolt. And then you would, to my mind, there's only high strength friction grips, but 8.8s will do the job as well, and 10.9s. Yeah, that's just my comment. I just find I only came in halfway through, so I may have missed the beginning statement. So I just found what was said a bit nonsense. Apologise, Mr. Rob.
Daniel, do you want to respond to that? And then we'll give Rob an opportunity.
Yes, just because now we're raising the issue of pretensioning bolts, which is an important topic in its own right. As Les correctly states, only a minority of structures require pretensioning. And a majority of structures do not require that, and a bearing connection is really good enough for most all connections that we do. The most typical cases where you need to pretension in real practice would be one is where I just mentioned, which is the case where you need a friction grip connection for some reason. A second case is also somewhat less mentioned a little bit, where bolt itself is loaded in tension and it's cyclically loaded. And the reason for that, as odd as it might seem, is when you design for fatigue, let's say when you design the bolt for fatigue, you're always dealing with stress ranges. Now I know David is also here, Dave Blythenthal, and a whole bunch of people who do a lot of these types of structures. And fatigue is real, Dave. It does happen and it does crack when you have something cyclically loaded. and you deal with stress ranges. And by pretensioning the bolts, you can actually almost eliminate the stress variations, even though you have cyclic loading. So it's one of these miracles of structural engineering. So those cases also you use for, that's one case where you do pretension. If you are designing, if you're doing a project in Chile, whatever, you're doing seismic projects, you have to pretension. So these are rare. That's why I'm actually itemizing them, because they're not the kinds of things you run into every day. And of course, you may also want to pretension when you have essentially the moment type connections with the plates that Les was describing. So I just wanted to add that to Les's comments. But Rob can also probably comment here.
Yeah.
Can I add another case of, say, a vibrating structure, you know, screen structures?
Is it just me freezing or something?
No, we've lost Les.
Okay.
my connection has disappeared. I'm sorry.
We opened the trapdoor when you disappeared. Sorry, could you perhaps just repeat that? And then I just want to give Rob an opportunity to comment as well. Les?
My comment was, yeah, the only other probably instance where I would really seriously talk about pretensioning bolts is on a screen structure, something which has got vibrations in it, which will slacken the bolt. They do, and it's just the name of the game. So therefore, a fishing grip or high tension bolt, fully tensioned. That's my only other comment as regards to using high tension bolts.
Okay, great, Rob. It's your moment in the sun here.
So I think that perhaps I just want to make sure that yes, I am. I may have misunderstood the direction of, or the intention of the talk. When I saw tension, I immediately presumed pretension, and I would agree with Les that the need for pretensioning, and also what Amanuel has said, is that there are certain applications. They tend to be high-risk structures. For example, bridges. Even bridges may not necessarily need pretension bolts, but it is typically in the cyclical applications, and also areas where they are regarded as high risks. For example, power stations, and you'll find in Medupi, Kusile, there's pretension bolts all over the place. So, and I think a lot of it also depends on the engineering who would prescribe or over-design just to make sure that they reduce any possible risks on them. But I would agree, the typical bolts that are used, they just need to be hand tightened or snug tight. And I recall the previous CEO of the South African Institute of Steel Construction said, well, you could go around with a set of binoculars to check that the bolts were okay. And that was all that was necessary. So thank you.
Right. Amanuel, do you want to perhaps respond to that? And then I'd like to see if there's anyone else that has any questions related to tension members or connections. If you want to ask a question, please just pop your video on so that we know that you'd like to ask a question in person. And go for it, Amanuel.
Just a question for Rob, a very complicated technical question. We used to say that snug tight is the full effort of an iron worker. I would like to ask Rob how strong that iron worker needs to be.
You're on mute, Rob.
So they talk about the average worker. So I've tested this out at work, and I'm well below the average worker, and as I've got a number of guys who are above the average. So it is subjective, but if you are talking about the friction grip applications, generally, if I snug tight and a tougher guy snug tight, the amount of the angle, there is quite a lot of leeway to ensure that you do get the pretension, and it's very unlikely that you're going to break the bolt.
Right, Emmanuel. I don't see anybody else with their camera on, so I'm going to assume that there are no more questions that are related directly to the topic we're covering today. But what are some of the other technical questions that have come up in the last couple of weeks that you'd like to highlight?
Well, the few that I've seen, and unfortunately in the one case now, there's been a serious collapse on a warehouse building. I've seen a lot of tension members that make use of, let's call it rods or cables for bracing of, let's say, industrial buildings. This is a project in Mozambique, and the thing didn't withstand the recent high wind conditions that they had. But the issue is one of when you use tension members in that way, typically there should be a requirement to pretension. Now, I want to ask John Barnard, in fact, how they do the straps, which are also tension members in light steel frame buildings, for lateral bracing. Do they pretension them or not? Because those are, I would assume, to be the most important tension members in, let's say, in light steel frame construction. So I'd be very curious to know what they're doing in South Africa in that regard, if John is still with us.
I'm not sure that he is. Let me just double check. I don't see him still on call, but that is a good question that we can perhaps raise in a subsequent Q&A session.
Yeah, because that's an area where people are using these tension members, cable type. Now, I'm not talking about angles. These are essentially cable type or rope type structures that are being used to brace buildings, where they're not necessarily pretensioning them in the specifications. So I've always been curious about how that works if you don't actually pretension it beforehand.
David, I see you've joined us, David Haynes. Do you have any questions that relate specifically to tension members or to connections?
Amanuel and Denise, thanks. We had a project about, I don't know, must be 7-8 years ago, where we had to specify a large tension member, and the aesthetic appeal would have been to put in a cable as a tension member. However, there were cost issues related to the end connection, but also the practical issues and the pretensioning and the amount of stretch the cable had.
Yeah.
And in place of the cable, we decided to use a flat bar.
Yeah.
Because a flat bar works, you bolt it up and it works with a full Young's modulus in accordance with the gross area, and the performance is known. It's very easy to achieve what your design intents in practice. Cables tend to be rather uncertain, because you don't really know how much it's going to stretch, how much pretensioning you've got to do, and to do it properly, you need things like load cells and the likes to achieve that. So flat bar is far more practical.
Yes,
Yes,
I agree with Dave, and there have been a few structures up that we've gone to visit, Denise, for Steel Awards, where the roofs make use of these types of tension members. And the one, I'm trying to remember where it was, I think it was in Sandton, that TAS Engineering did. It was very complicated to calibrate during construction. And of course, the problem is you calibrate one tension cable, and then you start doing the other one, and this one is now out. I mean, you really have to have a proper regime and program. And by the end, everyone gave up and tensioned everything, and just hope for the best. And it actually works, but it gets very complicated once these roofs are quite complex. And the connection, of course, was very complicated to the actual member. And that's always the complication with tension members.
I had that situation many years ago, putting up a guide stack. Guide stack was 100 meters high and had 6 guys onto 3 points. And each one of those points had a load cell. Each one of those guys had a load cell. So we were running around from point to point. And as the sun shone and the one side of the tower heated up, all the loads changed. So it was a bit of a job.
Yep.
Liz, I see you tactfully raising your hand there. Is there something you'd like to comment on? Just you are on mute at the moment.
Yeah, I was just thinking of a cage when you're underground, and the cage stops at a station. You see it bouncing because the rope is stretching, so that gives you a good idea of what rope will do. You could always go back to a very old-fashioned method which they used to do years and years ago, where they would take a rod, put it through the building, heat it up in the middle, tighten the nuts up, and then when it cools, the contraction pulled it back together. That was a very nice way of doing things a long time ago.
Yes, yes. That's very cool, because that also makes it very easy to actually find out about how much tension you've put in there, because you know your strains.
Yeah.
Yes, right. One thing that does come up with these kinds of systems that I have a question that was asked of me, maybe let's say 3 years ago already now, was the difference between using a rod and a cable. Because of course these cables are essentially little wires that have been wound into let's call it a rope. And of course, the way a rod would behave as compared to that wire, it's called wires actually in our industry, is very different, because those wires actually relax quite a bit. And it's not that the steel itself is creeping. So people always assume that the steel is creeping, which is not true, because steel doesn't creep much at ambient temperatures. It will creep at high temperatures, but not at ambient temperatures. But those wound wires actually do relax from just the way in which they're wound. And the guys who do pre-stress construction know about this quite a bit. And the relaxation can be quite serious, as in you can lose 10–20% of your strain easily and very quickly. And that relaxation can go on and on and on for 2–3 years. And you can almost lose all your, let's call it tension or pretension when using wires. So that's another question that has come up before, where people are trying to differentiate between using rods, wires, and what is even the difference between these types of things, of course. So there's a lot of confusion in that area as well.
Emmanuel, I read some years ago it must have been a Hagee catalog, and they actually stated that your effective elastic modulus, your effective Young's modulus for a cable, is approximately 50% of the equivalent solid steel section. So as a rule of thumb, when the guys in the office did structures with cable stays, we reduced the section area or the Young's modulus on that particular section to allow for that, and how it behaved at instantaneous deflection.
Yes, yes. So what you're doing is you're finding a proxy way by reducing the stresses, which is an interesting, yet another approach. Yes.
Yeah.
Yeah. The area where they do a lot of this kind of work is the folks who do pre-stress construction, and those guys have to get it right, simply because otherwise the slab doesn't behave the way that it's designed if they don't allow further relaxations in their design. Yeah.
Yes, that's right. And again, there's
Excuse me.
okay. There is a pre-stress loss formula portion that allows for relaxation.
Yes, correct.
Yeah.
In their case, they also have that complication of the fact that the concrete itself creeps in compression. So they lose a good amount of their pretension from that creep as well. So the problem is compounded in a way. This is a problem that we have also in pretensioned holding down bolts, which can also be in tension. So maybe that's applicable here. So when people do try to pretension holding down bolts, this is the kind of question that also comes up. they forget that the concrete will creep and that the pretension will actually reduce significantly in about 6 months, and that there needs to be some sort of maintenance regime installed. Or we've actually solved a method in the Green Book where I came up with a sleeve for those people who do have a Green Book with them. Yeah.
When you say pretension holding down bolts, do you mean for buildings or for major machinery?
The application where people are trying to pretension holding down bolts is for things like signposts, gantries, at least the questions that have come in. These are mostly like cantilever type of structures where they're trying to somehow attach that base to the concrete and pretension the bolt from, I think, from a point of view of trying to reduce propensity for fatigue cracking, because pretensioning a bolt in general, when you're doing steel to steel connections, works to reduce your stress range significantly. And they're trying to, I think, replicate that in that foundation, which doesn't work because that pretension is lost due to creep when it's pretension against concrete. So this is a question that has come up before a few times before, and I've referred to that solution that I have in the Green Book. Of course, it's a bit more expensive because you have to install a sleeve and this and that, so it's not as simple. But in that case, at least you're pretensioning against steel as opposed to concrete. So this is, and I've also seen them pretension, I think, base attachments for stacks. So this has come up a few times, but mostly in industrial applications or with gantries and things that are cantilevered, like columns that are cantilevered.
Okay.
When you turn to UL, a rock anchor is probably a good example of a pretensioned, when you're underground and you'll put these things in 2-3 meters into the rock. That's my own experience of those, that type of pretension.
So what do you do? Do you have to have a maintenance program where you go and pretension them every few months or what?
Oh, once you've seen this, you hope.
Oh, you just hope it works. Okay.
Yeah, otherwise it falls down.
Yeah, that sounds like the mining industry. Yeah.
It's pretty dark down there.
Yes. Yes. Yes.
Okay. I think that's it, I think.
Yeah. Denise, are you there? I think we've lost Denise. Any questions? Any comments? We have quite a number of attendees here who are very quiet. Any issues that have come up with the rest of the? I think we have 25 or 30 people here.
Manuel?
Yes.
Victor, yeah.
Ah, Victor, maybe I should have asked you about those straps for light steel construction.
I can maybe mention that a bit, but mostly I just want to say I concur with all discussion. If that will suffice.
Yes.
Now, Amanuel and I spoke earlier on when he allowed me into the meeting, into the Zoom meeting. And with the lightweight steel industry, I did some construction for a while, up to 2012 with that. And my major concern with the lightweight steel construction industry, and maybe it's not, doesn't fit this discussion, but I'm just mentioning that, is that the fact that the finishing materials, there's a monopoly in South Africa and they ask whatever they want. That is the first thing. So to try and market that, and then maybe John can come in if he's still here, but to market this, the lightweight steel construction with my clients is very difficult because you cannot tell them it's cheaper, because it's certainly not. And then my main concern with lightweight steel construction is that, and you were talking about straps there, Manuel, but there are so many of these contractors who do that, which think it's just, like buckyballs and what maybe. They have no clue what they're doing, and specifically with the vapor locking of the building. And secondly, when they introduce you, if you do your K-straps, for instance, you drill those holes yourself. There's no pre-drilled holes into the structure where you can attach your K-bracing to. And I've seen horrendous things where, for instance, the edge distances were not correct. And from my point of view, to be a structural engineer, I would hate to be a structural engineer on a lightweight steel construction building, because SAISC and XI expects us to inspect the whole construction works. And my question is, how do you inspect 2,000 or 3,000 connections? You cannot. It's simply impossible. So that's my contribution to this discussion.
Yeah, Victor, I think you raise a very important point, which has to do with designing tension members with light gauge materials. And unfortunately, I have to say that there is a dearth of knowledge about how to design light steel frame structures in our engineering community. Most people don't even know that there is actually a standard called 10162 Part 2 for the design of those structures. And of course, designing connections that are screwed together as opposed to bolted, which is another method of connecting those light steel frame or rivets. All of these are, at this point, I would say, not being designed. There are guys who design it using these robotic software systems, which is essentially sort of deemed to satisfy or maybe Agromont approved. But in general, that's an area where we're far behind. We do have the standards. Obviously, we have the coil and the producers, but the engineering is far behind. And those connection types are very vulnerable to tear out type of failure limit states, the type of stuff I was discussing earlier, where things can actually tear, because we're talking about materials that are less than 3 millimeters thick, typically. So we're talking about 1, 2, or 3 millimeters thick, sometimes less, 0.8. So Victor, I'm glad you raised it. And of course, that's why I was asking about the straps. It's too bad that John escaped and ran away before I could ask him this question. But I've designed a few of those buildings, not very tall or anything, just 4 or 5 story buildings, apartment buildings made out of light steel frame construction. And the most typical way in which you do the lateral system is using lacing. Essentially, these are straps that work in tension. And the connections have to be designed correctly, otherwise it doesn't work. And my understanding is they have to be pre-stressed. So I wanted to ask him how they do that here in South Africa.
The easy answer to that is they don't.
Okay. Okay. Yes. And of course, why these systems work, even though they don't pre-stress them, is because the sheathing itself, which is essentially the boards that are put on either side of those studs, provide a huge amount of lateral stiffness. So no one will ever notice that the thing was not designed correctly. That's, I think, the basic assumption here. It's similar to how sometimes, people forget to put in bracing in the roof, and the roof sheets do the work, even though they've not been designed for it. Unfortunately, in Mozambique, in the last few months, because the winds, this is the standard old saying, right? It works. Why does it work? Because nothing has failed yet. And of course, when people say that, I always say, well, that's because the structures hasn't been loaded to the design level yet. So, and those are low probabilities, but that's what we should be designing to. But in cases like Mozambique, now those structures were loaded to the limits that they were presumably designed for. And especially a lot of industrial buildings actually came down, meaning collapsed, not just failed, but collapsed. Because there's a lot of essentially either negligence or simply not knowing the various requirements for how to design these buildings.
If I can just say something else, there's a very low understanding of the relationship between risk and probability.
Yes.
Even though it's a low probability, it still stays a high risk.
Yeah.
The influence of the occurrence is very high, and that makes it a high risk situation.
Correct. The impact is very high. Yes.
So, folks, we've got about 3 minutes left. I just wanted to say that if you have any extra questions on this, we do have a specific email address that you can use for any technical questions to the SAISC. It's technical@saisc.co.za. Very creative. But if you've got any questions related to the topic we've been discussing today, or any other questions or comments or anything that you'd like to see in a future edition of these Q&A sessions, please pop it through to that address or to Amanuel. We do have these every 2 weeks. They're on the SAIC website under training. You'll see the technical Q&A sessions, and there's a list of the kinds of topics that we're looking at. And just remember, like, there's a broad discussion that happens in the beginning around a specific topic, but there's always an opportunity to ask any other questions that you may have related to the use of steel in construction, or any comments that you want to contribute. So yeah, I just want to thank you all for joining us on behalf of the SAISC. And we will be putting these recordings on the SAISC's website in the member login section. Attendance for the rest of the month and for the month of April for members and non-members is free. Always free for members, so you're welcome to join us whenever you like. And that's pretty much all that I have to say. Amanuel, is there anything you'd like to say in closing?
No, just thanks for coming. And I hope you enjoyed the discussions. Well, next time, come with your own questions or contributions so that it can be interactive. We see there's always, of course, the guys who are always here with opinions and questions and comments, which is excellent. That's what the intention of this is. So good.
Denise, may I ask a question?
Yeah, go for it.
What is the possibility of discussing structural insulated panels as an alternative construction method for next session?
I'll add that onto our session. We've got sessions planned up until June, where we've got specific topics defined, but there's always an opportunity after that main topic discussion to bring up any issues that you have or any queries that you have related to the use of steel in construction in whatever capacity. So what you're curious about, bring your questions, let's have those discussions. This is also a really great ground for us to get some feedback on the kinds of topics you'd like for extended sessions or training courses or webinars, or something that's a little bit longer than this. We have kept this to a 1 hour kind of time limit, because it's kind of a snack, your lunchtime snack that you can have of steel construction. But we're open to ideas for future sessions, topics. This is really about us engaging with the engineering community and with specifiers to share the expertise that the Steel Institute is renowned for. So any questions, any comments, any suggestions, just pop them to that technical@SAISC, and we can look at incorporating those suggestions in future sessions.
I would also like to see the lecture that Victor is proposing on the strength of insulated steel panels, cladding panels.
Okay, fantastic. Fantastic. Great. Thank you so much. Have a great rest of the week, everybody. And we'll see you in 2 weeks' time. Bring a friend, bring your colleagues. It's always great to see people engaging, and steel is a topic we're passionate about, and we can see that all of you are too. So we'd like to just build that and share the knowledge that the Institute has.